Okay, see, symmetrical component. How many of you know this symmetrical component? See, basically, in symmetrical component, we have positive sequence, then we have our able to see the screen.
Yes, sir.
Yes, sir.
Yeah. Okay, we have positive sequence, we have negative sequence, we have zero sequence. Okay, okay. See, normally this is our generator, no? This one. Now this generator, this is the generator. Okay, this is a three-phase. So, see, normally I have a three-phase system. My three-phase system consists of what? This is RYB, right? This is the three-phase system. I can convert, yeah, no. I can convert, okay? See, this three-phase system, RYB, I can convert it to three system, that is one with the same way. This is a positive sequence network, which I will call it as 1. Then we will have a negative sequence network. You know, in negative sequence, you don't have voltage. Okay. I call it as 2. Then I will have similarly a zero sequence network. I will call it as 0. I'll explain you how to do this. Okay.
Sir, are you recording this?
Yes, sir. It's getting
You
recorded.
started. Okay, sir.
Okay. So now, basically, three-phase network will convert it to three independent. This one means I will explain again in one more method. Suppose I'm having my generator here. Then it goes through, let's say, a transformer. Then from transformer, it goes to a transmission line, right? This is the transmission line, this is the transformer, this is the generator. And here, let's say, there is again a transformer, and then let's say there is a motor here. Okay. One very important thing what you need to know in when you are doing positive is zero symmetrical component. You should know about the symmetrical this impedances, positive sequence impedance, negative sequence impedance, zero sequence impedance. You have to know this. Why we use this symmetrical component? Basically, we use it for fault calculation. That to the unsymmetrical fault. For example, I have a single line to ground fault, LG fault, or a LL fault. Okay, to study this, we are using the symmetrical component. Okay, now for a generator, normally the zero sequence, positive, negative sequence impedance is given by the vendor. If vendor has not given, you can make some assumption. For generator, you can take it as XD double dash, okay, Z1. And Z2, it is very approximately like ZD double dash only, or it is ZD dash plus ZQ dash by 2, something like this. This particular thing I will check and let you know. But what I found last time, one generator positive sequence was like 16%, negative sequence was like 17% or something. And zero sequence, the generator data sheet will give it. It will be something like 8% or something. Why zero sequence impedance is less? I will tell you. See, if you take a generator, no, the positive sequence, positive sequence and negative sequence, I will tell you the difference. See, positive sequence current will flow, let's say R, Y, P. Negative sequence current will flow like R, Y, B. In other words, negative sequence is, anti-clockwise. Since it is anti-clockwise, negative sequence current will create in a rotating machine, twice the speed, the rotating mm. Zero sequence impedance, all three current will be in phase. Since all three currents are in phase, what happens? It will very small amount of current is induced in the rotor. Because of that, the impedance is only due to leakage reactance. That's why it is low. Okay. So where do you get all this impedance? You can get it from the inverter. Now for transformer and transmission line, positive and negative sequence are same. There is no difference. Okay, because there is no this phenomenon like rotating magnetic field also. Now zero sequence impedance for transformer there is a trick, a little tricky. I will explain separately. And the zero sequence impedance for transmission line will be slightly different. Okay, because when zero sequence current flow, it will flow through the ground. Because it flows through the ground, I know it will be higher. And that there are formulas to determine the impedances for that. And for motor actually positive, negative are almost same, and zero sequence impedance for motor. If it is a synchronous motor, it will be similar to our generator. Okay. Now transformer, I will draw and show the typical for transformer. See, what I will do is I will tell you the reference where you can do further reading on this subject also, because this subject, to read it takes almost, I will tell you, minimum, I think 3 to 4 weeks you have to spend time if you want to learn symmetry component. See, suppose what are the transformer you can have? You can have delta star grounded, or you can have delta delta, or you can have star grounded, star grounded. Okay. Now for this, I will tell you how the zero sequence impedance. Okay, for this, it will come like this. And see, for this, for star star grounded, the zero sequence will be like this. For delta delta, it will be like this. Okay, and for not like this, it will be like this is how it is, because whenever you have a delta, the this one current will circulate inside. Okay. This is how. So now, okay, keeping this. Hold on, just 2 minutes. Now, keeping this in mind, let us see how do we do the fault calculation. Okay, I will come straight to the fault calculation. Everybody able to see and hear, right? Pinaki ji, able to see, able to hear?
Yes, sir. Yes, sir.
Okay. Naveen Kumar, have you been using symmetrical component fault calculation earlier?
Earlier to software generated values only, sir.
Okay, sir. Okay, sir. Lognathan, sir, you are using the symmetrical component earlier? Okay. Lognathan, sir, you are there? Okay. Inamulji, you used this one earlier?
No, sir.
Okay. Now, okay, let us see what you have to do. Let's say I have a single line diagram like this. Suppose there is a single line to ground fault here, okay? Now, first is you have to write the impedance of all this. What is the impedance of this? Okay, let me draw this like this. The impedance of this is XT double dash, let's say 0.16. Transformer is 7%. Let's say transformer is 7%, 0.07. Okay. Now let's say my cable impedance here was 0.02. Actual cable impedance in per unit, I got it. Now similarly, this one was, let's say, 0.03. Now motor also will have some impedance. Even the starting of the motor, that's the impedance. Let's say the motor was 0.0504 or 0.04 or something. Actual impedances, how to calculate? Actually, you have to get those impedances, okay? Whatever single line diagram you have, you please add the impedances, okay? Now, to get positive sequence impedance, okay, what you have to do, the positive sequence network, make this one. Motor, okay, leave this. Now, this is the positive sequence network. The negative sequence network, okay, now let's say, to draw the negative sequence network, what do? I will draw the negative sequence impedances here in the same way. I told you, okay, what is the negative sequence impedances actual value? Either you get the actual value or you make an assumption, okay? Let's say the actual value here is 0.17 and transformer normally positive negative is equal. This is a cable also positive and negative will say. Cable and transmission line, whether current RYB flows or RBY flows, the impedance offered by that cable will not vary. Okay. Now motor, there will be slight difference, but that can be neglected. Okay. Now next is I have to add similarly for the transformer. Let's assume it is a delta star grounded transformer. Okay, so I will add here. This is the system. Now for what will happen to the transformer here? This will become open. Here it will be like this. Because there is a delta here. Okay. And I come here, then I have like this. Now what is the zero sequence impedance of this generator? It was 0.08. For the transformer, I need to get if the transformer was grounded, let's say I need to get the zero sequence impedance. Let's say it is 0.05. And for the cable also, it is not much difference, positive, negative. See, cable, if the current flows to the armor, if there is a fault, the current will flow through armor, and if it's an armored cable, okay, now it will be 0.03, this may be 0.04. Now motor, as I told you, for motor also behavior is similar to a generator because it's like a rotating machine. So zero sequence is mainly influenced by the leakage reactance. Okay. Now, single line to ground fault. I want a fault here, right? If I want a fault here, what I have to do? I have to create a Thevenin's equivalent network. Okay, Thevenin, the equivalent network. So what I do, I have to see what is the impedance here. Okay, so for that, what I will do? I have to short all this like this. Okay, if I have to short all this like this, and I have to open. Okay, and then I have to see what is the impedance here. Then I can get the, how do I do? So 0.03 plus 0.03 is how much? 0.07. Okay, 0.07. So similarly here 0.07 plus 0.16 is how much? 16 plus 7 is 23. So this is 0.23. Okay. Now these two, so this one will become something like this. It will become something like here. Okay. It will become here 0.23. So 0.23 parallel with 0.07. What is the impedance? Anybody can calculate and tell me approximately. Pinaki ji. 0.23 ohms in parallel with 0.07.
0.23 in parallel with?
0.07.
1 second, sir.
Yeah. You can tell in the meanwhile, okay, let us add this 0.02 and 0.04. This becomes 0.06, okay. Now, let our Pinaki ji tell what is the impedance.
Yes, sir. 1 second, sir.
Yeah.
0.05367, sir.
0.05, okay, I will take it as 0.053.
Yeah.
Okay, so now this one becomes something like this. 0.053 and 0.06. Okay, so I need to know the impedance here. So it is series of So let me add 0.06 and 0.05. It will be how much?
0.11.
0.11. Okay.
1.
So basically now here the Thevenin's equivalent network will be like this. 0.11 ohms, 1 per unit. Okay. And here, okay, and it is like this. Okay. Now similarly, here negative sequence was almost same, right? Not much difference. So the negative sequence network is also similar to this. It is 0.113. Now zero sequence, how do I do? Let me open here. Let me check now. Okay, let me draw this as equivalent 0.04 with 0.06. This is 0.04 with 0.02. Sorry, this becomes 0.06. This becomes 0.05. Okay, this one becomes here, and here it's an open, and here it is 0.05 again. This one is coming here. Okay. And this part is coming here. Okay. Okay. Now this one, if I do the network, what is 0.06 parallel with 0.05?
0.06 parallel 0.05, sir. 1 second, sir.
Yeah.
Point 0.027, sir.
Okay, 0.027. So this becomes 0.027. So 0.05 plus 0.027 is 0.077. No, 0.05 with point,
Yeah.
right? Point double zero seven. Okay.
0.17. 0.17, yeah.
0.77.
No, sir. 0.15 plus 0.027.
No,
sir.
0.05.
0.05. Okay, sir.
Yeah. So now,
0.07.
okay, now see here, let me run rub the other thing. So basically now here, I have three sequence network, okay? Now this is the positive sequence, negative sequence, zero sequence network. Now if it is a single, okay, after this we again log in for just 5 more minutes, okay? If we have a single line to ground fault, we may have a line to line fault, we may have a double line to ground fault, okay? If it's a single line to ground fault, you have to join all three networks in series, positive, negative, and zero, okay? Positive, negative, and zero. And here is the fault impedance ZF, and that will give you the current. Okay, then you have to multiply. That will give you the current, which is I0 equal to I1 equal to I2, and the fault current, the phase current will be 3 times this one. Okay, and if it is a line-to-line fault, you have to add the positive and negative in parallel. Okay, yeah, line-to-line fault. Okay, now for me right now, see, for me this is very important. Okay, I will concentrate on this. So positive sequence impedance is how much? 0.11. Now negative sequence impedance is also 0.11, and my zero sequence impedance was how much? 0.077. Add all these three, how much you get? Okay, and let me have my okay. So at the positive sequence side, I will have my this one voltage source also. Okay, this is the fault impedance. Now 0.11 plus 0.11 is 0.22. 0.22 plus 0.077 is 792. So the total impedance, this one becomes how much? It becomes 0.0297. Okay, and let's say the fault impedance is very less, 0.001. Okay, so the total impedance, then it will become 1 per unit. Okay, it will become 1 per unit, and the impedance here will be 0.03. Okay, so now 1 per unit divided. So what is I? It is V by Z. V is 1 per unit and Z is 0.03. 1 by 0.03 is how much? 30. So the current will be 30 times the base current. Suppose the base current was, let's say, 1 kilo amps. So suppose the base current, okay, 30 times. Now, what is the fault current? Fault current is nothing but 3 times this 30. So it is 90. Now, suppose the current was, let's say, 500 amps base current. So it is 90 into 500, that is 445 kilo amps. Okay. So this is how we do the symmetric components. And I know, it is too short to explain this subject Actually, I will. You please refer this book by Stevenson. You will get a very good understanding on this subject.